Okay, let's return to our int cell one more time, and this time let's investigate what we call the big five operations. These big five operations are operations that come for free with any C++ class that you define, meaning you don't have to actually provide their definitions. The C++ language does so for you. Although these default definitions don't always work for us. Let's take a look at an example of when they don't work for us. We're going to take another look at the Int Cell class here, and this time when we look at our stored value, rather than having a simple integer to contain the stored value, we're going to use a pointer to an integer. Notice the asterisk in between the int and the stored value. This is indicating that stored value is a pointer to an integer, meaning the contents of stored value is now an address, and that address is the address of the value, the int value that we're trying to reference. This is going to mess up the big five for us. If we have any attributes that are pointers to things, we need to take care of rewriting or redefining or actually defining beyond the default implementation the big five for us. So to recap, the big five operations are basically what we call the copy constructor, the move constructor, the copy assignment operator, the move assignment operator, and the destructor. The copy constructor is used to create a new object by copying the state of an existing object. The move constructor is used to create a new object by copying the state of a temporary R value, which is discussed in another lecture and in the textbook, in the Weiss textbook. The copy assignment operator is used to change the state of an object by changing it to the state of some existing object, by copying that state into the one that's being changed with the assignment operator. The move assignment operator is used to change the state of an existing object by copying the state of a temporary R value object into this new object with the assignment operator. And then finally, the destructor is used to is called upon when an object goes out of scope and is ready to be removed from the heap. So one of the things that you need to be sure you're understanding from this, at a minimum, are what the method signatures of these big five look like. Secondarily, you ought to know when they're used and why they need to be defined in cases like this, when we have attributes that are pointers to primitive data types. So let's take a look. It's very simple. There's not much changing here. The only things that really change are the fact that stored value is being assigned an address by calling new. So instead of just passing along the initial value, what we're doing is we're creating a new integer based on that initial value, and the new keyword or operation I should say, is actually giving you the address of the memory location on the heap that stores this integer value. And again, that's necessary because our stored value is a pointer to an int. That changes the way we implement read, because now we can't just return stored value, because stored value is an address. What we need to do is dereference the value at that address. And so we do that by placing the asterisk in front of the pointer variable, right? It's called dereferencing the pointer. And this gives us then the integer at the address stored in stored value. And then finally, same thing with the write operation. We can't just assign the value x to stored value because x is a number, stored value is supposed to be an address, so what we need to do is dereference that address and put that integer into this dereferenced location. So it looks innocuous, but it's going to have a big effect on what happens when we use it. So if we take a look at a typical usage in figure 1-17, for example, pretty straightforward. Main is simply going to call this function f, and f is going to declare some int cells. Those int cells are based on the declaration and definition, if you will, provided in what we just looked at in figure 1-16. The pointer implementation, by the way, if you want to refer to it that way. And so we've got an int cell A whose initial value is 2. We have another int cell B, and B is being assigned the state of A. So we would expect B to contain the number 2, to store the number 2. And then we have another int cell C, who is not being initialized in any way, shape, or form. So at this point on line 14, it has the number 0 in it. So B is an example of what we would say is the utilization of the copy constructor. And then line 16 is making use of the copy assignment operator. So at anyways, on line 17, we are changing the state of A by writing the value 4 into it. So we would expect at this point that A contains the number 4, B contains the number 2, and C contains the number 2. And when we print this out, let's take a look and see what we see. So to compile this, it's pretty straightforward. We can just say g++ figure 1-17.cbp. We don't have to worry about any other implementation files here because the int cell was defined in line in the header file, which is included in figure 1-17. Compiles just fine, and when we run it, again, we're going to see a printout of the contents of A, B, and C. We would expect them to be 4, 2, and 2, but instead they all seem to be 4. So in other words, when we wrote the value 4 into A, it actually did change the value of B and C. And this has to do with the fact that those encapsulated attributes, stored value, were pointers to things. And so what we did was we copied pointers in our copy assignment operator and in our copy constructor. And it was the values that were changing, but the addresses didn't. And so herein lies the problem. This is, again, a big call for us to actually define the big 5. So let's take a look at how we might do that. Figure 118 shows us the big 5 and typical implementations in this situation. We have our int, here's our constructor, and we have our initial value, and this is no different than before. Now here is our destructor. So one of the things we need to make sure that we're doing in our destructor when we have an attribute that is a pointer is we need to make sure that we're returning that memory location to the heap that we took away from the heap on construction. So in other words, here on line 16, we allocated some memory space on the heap to store a number. Now, when this object of this class gets destroyed, we want to make sure we return that memory back to the heap, and we do that by calling the delete operator. So this is one of the things that we need to take care of if one of our data members is a pointer. We need to make sure that we're returning that memory to the heap on destruction. Here's our copy constructor. You need to know this method signature. This is the method signature for a copy constructor. It is a constructor, so its method name is the same as this class name, in this case int cell, and the argument here is a constant reference to such an int cell. So in this case we're calling that reference RHS, as in right hand side, and what we need to do is make a copy of what is stored in that parameter. So the parameter is dereference. You see that in star RHS. That gives us a number. So star RHS dot stored value gives us a number that's stored in that cell. We take that number and we're creating a new memory location to store it. And it is that new memory location's address which is being stored in this new object that's getting created. Our move constructor, this is the signature. All right, this is the signature you need to know. Here it's a constructor, so again the method name is the same as the name of the class, in this case int cell, And the argument here is a special kind of reference. It's an R value reference. Again, this is discussed in another lecture and in another section of Weiss. And so it's different, right? The 2 ampersands is different than the 1 ampersand. And what we're going to do is simply move the value from the argument, which is just a temporary object that's being passed in. And we're going to take the value that's in that temporary object and copy it into the stored value. Here, no dereferencing has to occur because we're copying a pointer into another pointer. RHS.storedValue is a pointer. We're copying that thing into another pointer, this object's pointer called stored value. And when we're all said and done, we want to do some good housekeeping, and we will then set the temporary object that was passed in, its stored value. We're going to set it to the null pointer. So this is just a standard boilerplate method for implementing your move constructor. Then our copy assignment operator, its method signature looks like this. You need to know that method signature. All right, you need to be able to identify this method signature as being the method signature of the copy assignment operator. All right, so assignment operator, this is a way that we overload the assignment operator, the equal sign, if you will. It's going to take a single argument, again, a constant reference to said object. We'll just call it RHS again for right-hand side. And this method is returning a reference to an int cell. The reason we return a reference to an int cell is so that we can cascade the assignment operator, so that we could say something like x equals y equals z equals blah, blah, blah. And that cascading of the assignment operator is accomplished because the return value of the assignment operator is a reference to an int cell. Now the first thing we'll do is just making sure that we're not doing what we call self-assignment, that we're just assigning, say, x equal to x, or a equal to a, or whatever the case may be, because no work needs to be done in that case. If that's not the case, all right, if this, and this is a keyword, which is a pointer to the current object receiving this message, i.e. the left-hand side of this assignment operation, if it's not equal to what's on the right-hand side, and the ampersand here is being used to get the address of this argument. If the address of the right-hand side is not equal to the address of this object, then they're different things. Let's go ahead and copy the integer values into the integer value, right? That's why we're dereferencing here. And then when we're all said and done, a reference to this object is simply obtained by dereferencing the pointer to this object. The move assignment operator is done a little bit differently. What we need to do is basically take the contents of the parameter, the R value reference that's being passed in, and copy, or swap, I should say, move the contents of the temporary object into the current object, the left-hand side of this operation, if you will. And then once we're done with that, swap takes care of this kind of thing of setting the temporary object stored value to the null pointer, so we don't have to worry about it. And again, just return a reference to this object when we're all said and done by dereferencing this pointer. Our read and write operations don't change. So these are the big five again. The destructor, and you need to know the method signature of a destructor. It's basically the tilde character followed by the name of the class and no arguments. The copy constructor, which looks like this. The move constructor, whose method signature looks like that. The copy assignment operator, whose method signature looks like that. The move assignment operator, whose method signature looks like that. And those are the big five. And when you have a class that contains a data member, which is a pointer to something, we need to take care of the big five in a manner similar to what we've seen here. So let's see how that fixes the problem. Let's go back to this here, and instead of using the definition provided in figure 118 or 116, let's give this new improved definition that actually provides definitions for the big five and rerun this program. So I'm including a different implementation of Int Cell. Nothing else changes. It's still called Int Cell. It's just a different implementation. And if we compile this again, it should compile. There's really no difference. But now when we run it, we see the correct expected values, 4, 2, and 2. And the magic here is that the assignment operator, the copy assignment operator, and the copy constructor made copies of the values that were being pointed to by the right-hand side objects in those cases. And there you have the big five.